Hi everyone and welcome to my channel. This is Maan and thank you so much for having me part of your day. So let me start with the question, what do we have for a portfolio of happiness? As an entrepreneur in 40s, there are a lot of elements to consider in seizing the moment for happiness. To start, we have to be comfortable under our own skin. We have to define the things that will make us authentically present and happy. And this helps in creating our personal brand. Second, we have to embrace that we have to wear multiple roles and wear multiple hats being an entrepreneur, and that makes entrepreneurship very rewarding. And the intention behind the servicing, okay, for the community matters a lot. It answers the question, why are you doing what you are doing now? So they say that we have to perceive things positively. Personally, it's more than that. It is about being forward-looking. Okay, we have to see opportunities. Okay, we have to capture what makes us happy, what makes us productive. Okay, so we try to look for selling opportunities. As a vaulted player, being in a bench is actually an opportunity to cheer for the team. Raise the score, raise the score, raise it, right? And just be present with the team. Learn from your teammates, from the opponent, learn from the totality of the game. So time on the bench this pandemic is an opportunity to acquire skills for online presence and personal brand. So why acquire the skills and content, Maan? Well, the intention has this discussion point. There is indeed a spirituality in the arts and science of selling and teaching. Okay, so pardon me if the choice now is to acquire beautiful online contents that would express my personal authentic self to each one of you. So thank you so much for watching up to this point. So next, I'm going to share a documentation, okay, about trigo function, radians, and transformation, okay, of these trigo functions. Would you like to know how to illustrate these trigo functions, the concept of radian for our learners to understand, no? Why is it pi equal to 3.1416 and what have you? All right. And would you like also to know how to explain transformation of trigo functions using GeoGebra? Interesting? Yeah, indeed. Okay, so please do watch it to the end. Okay, I'll make it so much fun and easy to follow. Okay, and thanks again, okay, for having me part of the day. So yes, hi friends, so let's proceed. Okay, so in the previous episode, we have learned the elements of the unit circle and we relate it to trigonometry. Okay, so circles and triangles are the foundation of geometry. It is the simplest form. Okay, so if you want to study quadrilaterals and the other geometrical figures, you can break it down to triangles. Okay, so it's the simplest form, the smallest form. Alright, and on a side note, this reminds me on the basic principle of drawing and sketching, and that is to break down a subject, okay, into smaller geometrical figures to achieve proportions, because indeed there is a lot of math in nature. Okay, and you break it down into smaller circles in order to achieve good proportion and good symmetry. Alright, so through geometry and math, our natural world is filled with beautiful proportion and symmetry. My daughter told me yesterday that as a beginner on sketching and drawing, we have to continue studying objects in order to have a great grasp on what makes sense in the natural world in terms of shape and colors. Okay, so as always, geometry is the artistic side of math for me. And there's also art, no, in sketching functions or sketching graphs. So just like art, the innate nature of different trigonometrical functions beautifully makes sense. It is mostly predictable or always predictable. And just like math, life has its own share of mystery though. Okay? It has a lot of surprises and unknowns. Alright? And these unknowns can be discovered in the near future because we have this amazing human spirit. But again, okay, in math, there are also unknowns. So today, let me take you on a different transformation on the different trigonometric functions. So first, I'm going to demonstrate how to prepare a graph, prepare the x and y tables, and then sketch the functions using GeoGebra. And then the second part will be a demonstration on how to transform graphs, okay, by having various coefficients for A, B, and C, or various constants or instances of the variables A, B, and C in the graph, okay, using the standard form for each trigo function. And later on, we will going to describe a radian. Why is it a pi is equal to 3.1416? And how we can use GeoGebra to illustrate what radian or rad is to our learners. Okay, so please do stay with me. Let's have fun, okay? Alright, hi there. Thank you so much for staying again. So let's proceed. So this is just a documentation, okay, on how I managed to describe special angles and then get the trigo ratios, okay, of these special angles, and then how we plot the x and y values for a sine function in GeoGebra. Okay, so this is just a teaser. Basically, I am encouraging my learners to be able to build this on their own without memorizing. By just understanding the trigo ratios, the trigo function, you would be able to handle this and create this table on your own independently. Okay, so let's start that session. Definitely, I'm going to discuss this here. Okay, have an online tutorial for that. Okay, so I'll be discussing all of this here step by step. So, but my focus now here is to tell you guys that in Excel, we have the sine function, the cosine function, the trigo functions here built in. But the x values, okay, of the sine functions should be numbers. And it should not be angles in degrees or angles in radians. So let me show you that it should not be angles in degrees and angles in radians. Okay, so for example here, sine 30. Sine 30 is 0.5. So if we assume that the sine function here will accept an x value of an angle in degrees. Okay, so your x value angles in degrees. So sine 30 degrees, for example. So sine 30 will return as negative 0.98. Does that make sense? Because sine 30 is actually 0.5. Okay, so what we need to do then is to convert the angle in degree to radian and then radian to numbers. Okay, so for example 30. So how to convert 30 degrees into radian? So we just have to divide by 180 because 1 pi is equal to 180 degrees. Okay, I hope we're clear with that. So we have 0.16. Now, this 0.16 has a unit of measure pi. So 0.16 pi. So we need now to convert pi to its numerical equivalent, 3.1416. So 3.1416 times 0.66. Okay, so you have here 0.5 or 0.52. Alright, now we will going to, that is now the numerical value. So the sine for this value, which had been derived from the special angle 30 degrees, is 0.49 or 0.5. So it now makes sense. Okay, so in building trigo function graphs manually, we have to create this table then. Okay, wherein the x here have been converted to radian, and then radian to the numerical value x. Okay, are we clear with that? I hope it's clear. Okay, and then you have here different coefficients A, B, and C. Here A is 4, 3, 2, 5. Okay, and we have B equal to 3, B equal to 0.5, and C equal to 180. So in transformation, basically guys, the concept there is that we would be able to sketch in our mind, okay, how the graph will look like, okay, if we have coefficients A, B, and C. The standard form of a sine graph, for example, is y equals a sine bx plus c. So an A here would describe the amplitude, the highs and the lows, or we will going to discuss that later on. So basically, A, B, and C would impact how the graph would look like. The simplest form is y equals sine x. So if you have coefficient A, then how would your sine wave look like? If you have coefficient B, how would your, or C, how would your sine waves look like? So that's the basic, the concept of transformation. How the sine wave, cosine wave, and tangent, cotangent, cosecant, and what have you will transform once we have introduced coefficients. Okay. So after converting now, you have here the x values, okay, as a set of numbers, not a set of degrees, angle in degrees, not a set of angles in radians, but set of numbers. Okay, and you have here your y you have here y, okay, using the sine function. Okay, so if you double click it here, yeah, so we use the function sine. Okay, and then 4 is your a, so you multiply in 4, okay, like that. So you now have here the y value. So this is our x in numbers, y values in numbers as well, and that would represent the function. Okay, the different function y equal to 4 sine 3x, or y 4 sine 3x plus 180, or y equals 4 sine 0.05x. So here our a is 4, b is 3, here a is 4, b is 3, c is 180, a is 4, and then b is 0.5. Okay, so I hope this is clear. Alright, so hi everyone. So thank you so much for staying up to this point, up to this part of the video. So in this segment, we'll be describing radians, and then we would know, okay, why is it that pi is equal to 3.1416. Okay, so let's discuss those. Let's start the story by appreciating our legends long time ago. Okay, so our mathematicians before, when they tried to answer these questions, their questions for good measure, they managed to describe components of a circle, of a triangle, compare those elements, and once they find meaning from those comparison or ratios, then they defined it. Okay, so just so happened that yes, they have discovered a relationship between the arc length and the radius, and they defined it as rad. Okay, so what is rad? Basically, it is a ratio, okay, of the arc length to the radius. So if we have 0.5 rad, it's telling us that the arc length is half than the is half of the radius. Okay, and if our arc length, if our angle, by the way, is 1 rad, then our arc length is equal to the radius. Okay, and then if we have 2 rad, this one, then the arc length is twice longer than the radius. This one is 3 rad. So the arc length is twice longer than the radius. And if we have 3.14 rad, we have an angle that is equal to 180 degrees, or the straight line. Okay, so we have an angle pi here. Okay, so from 180 degrees, convert that into radians and express it as pi, and pi is equal to 3.1415. Okay, because if you compare the arc length with the radius, okay, and then you have an angle of a straight line, then it is equal to 3.1415. So that is a numerical value of 180 degrees, or pi. Okay, so moving along, you have here 4 rad. Okay, so 4 rad means the arc length is 4 times longer than the radius. Okay, and then we have here 5 rad, so the arc length is 5 times the radius. This one 6 rad, okay, and this one is 6.28, okay, or 2 pi. The angle is 2 pi, and in degrees, that's 360 degrees. And in numerical value, that's 6.28 or 6.27, something like that. Okay? So I hope that this now makes sense to you. Okay? That we can actually express angles in degrees, in radian, and then in numerical value. And why do we need to have the numerical value? Because our Excel spreadsheet accepts or considers the x values to be a set of numerical values and not a set of angles in degrees, not a set of angles in radian. Okay? So after the converting, then we can put that in our spreadsheet in Excel, migrate our Excel, okay, after we're doing the conversion, okay, right, the one that I discussed a while ago, then we migrate the data, the x and y values, to the GeoGebra Classic spreadsheet, okay, and let GeoGebra do the plotting for us. So stay tuned, okay, I'm going to demonstrate how it has been done. Okay, so thanks. Yes, hi everyone, and thank you so much for staying up to this point. So we are now at the segment where I'm going to demonstrate how to migrate your values from the Excel, your X and Y data set, to the GeoGebra, so that the GeoGebra can help you sketch the graph according to your data set. Interesting, right? So, but then I would challenge everyone to try to do it manually. Okay? You buy a graphing paper or something, and if you want to validate your work using the graphing paper, then you can also let the computer do the sketching for you, okay, or for the team. So it's a computer-aided sketching. Okay? So we have here the data set. So we'll every now and then I'll be moving the video. Okay, so this is now my X value, the set of X values, and the yellow ones are the Y values. Okay, the Y values for the function for sine 3x. We also have for the function sine x. We also have the function for sine 3x plus 180, and we have for sine 0.5x. Alright, so let's go and have some fun. We'll do the migrating, so we'll start with this one here. Okay, and then we'll go to GeoGebra, And then we'll go to classic, okay, and then open a spreadsheet. Alright, so the spreadsheet is where you will going to input the values. So okay, there's the spreadsheet. So and then we have our y value here. Another y value here. Okay, so this is for the function for sine 3x. This is for the simplest form, sine x. Okay, and we also have this one for sine 3x plus 180. Okay. And the last one is this one for sine 0.5x. So the data set, we're going to consider all of the angles, okay, or angles from all of the quadrants. So that's why there are a lot of values you can see. Okay, so I'm trying to capture the entire unit circle and another revolution of the circle, something like that, so that you will have like a lot of waves, okay, because one period, one high and one low would mean one revolution of the unit circle, right? Okay, so let's do the x and y. So this one, the simplest one here. So in calling the point, you just have to start with a equal sign and then call the x value and the y value of the function. There you go, it's the origin. And then you just have to drag it going down, okay? So let's just wait for, there you go, see? You can now see in the GeoGebra Cartesian plane the data set, okay, sketching the graph. So beautiful. Alright, and let's now move on to the next function, this function. Okay, so that will be y plus 4 sine 3x. Okay, so equal sign again, and then the x value, oops, enclose it with a open and close parenthesis, so x value, and then we have the y value. Okay, so here in y plus 4 sine 3x, our a is 4. Okay, so observe the height and the depth of the sine wave. Okay, and we have 3x where b is equal to 3. So I'm just going to drag this down. Oh, there you go. So what can you see? What can you say now to the height of the wave and the depth of the wave? Okay, so the height is high. It's higher than the standard, the simplest form, right? The height is higher than the height in the simplest form, and as you can see, it aligns to y equals 4, right? So 4 is the amplitude, okay, and the depth y equals -4. Okay, so the a will tell us about the height and the depth of the sine wave. Okay, so by just looking at the the function and having yourself familiarized with transformation, you can actually visualize in your mind how the graph would look like. So that's the agenda here when we try to discuss the transformation of the graph. Okay, because it has been observed, so it has been documented in our math books. Alright, so the next one here is this one. Okay, so y is equal to 4 sine 3x plus 180. So equal sign, and then you call this, no, sorry, the common x values, this one, and then 3x plus 180. Plus 180 plus 1. Okay. So what would be the impact of the 180? Okay, so let's observe. Okay. So drag it down, just like an Excel. So we have A, okay, as 4, B as 3, and C as 180. So somehow it would be, so let's try to differentiate the two. So we can add colors. So this one, 3x. We're going to make this green. Ta-da! Okay, alright. And then this set of data points, set of this function, set of points for this function, 4 sine 3x plus 180. So there's 180, right? Okay, so we were going to use the color red, for example. Okay. Alright, so what have you observed? So there's just a sudden shift, okay? So from the green one without the 180, without the C equals 180, and then the red one, we have C equal to 180. So the same amplitude, the same narrowness, okay? But it shifted to another place of the Cartesian plane. So the C, we're going to contribute the shift, the movement of the sine wave to the left or to the right. So we will discuss that in another segment, the transformation of the triangle function graphs. Okay, so I'm just letting you see it in your own eyes visually that yeah, it shifted to the right. Okay, so the last one here is 0.05. Okay, we don't have a C, B is 0.5, and then A is equal to 4. Okay, so we will going to call the common X. I know that we have to move on, but in math, it's okay to talk about your X. And then we have this one. And then it's okay also to ask the question, why? We have to find the answer of the whys, right? Okay, and now for the last function. Okay, that last function is y equals 4 sine 0.5x. So amplitude A is equal to 4, and then B is equal to 0.5x. So please let us observe together how this graph would look like. Alright, so we'll call the X. Okay. And then this is now the widest one. Okay, and then we're going to drag this one down here. Okay, so we now have the sketch in the partition thingy. So try to observe the width of sine wave, okay, and compare it to the wave of the function where we have b equals to 3. So this one, b is equal to 25. Okay, and this one, the red one, has b equals to 3. Okay, when you have a color for this, so let's say pink. Alright, so the pink graph is very wide apart, okay, because our b is equal to 2.5. It's a very small number. And now the green graph and the red graph has b equals to 3. It's a bigger number. 3 is bigger than 0.5, right? Then the sine wave is very narrow. Okay, the bigger the b, the narrower the sine wave will be. And the smaller the b, the wider it will be. Okay, so this now ends my demonstration. Again, how to migrate the data from Excel to GeoGebra Classic so that you can appreciate the graph that we just have sketched with the help of GeoGebra. Okay, considering the data points that we have prepared in Excel. Okay, so I will just prepare another episode, and that is to discuss the different transformations of the different trigo functions. Okay, so I hope that you have fun with me. All right, and have a good one. Happy blessed Sunday, everyone.